In this tutorial, we're going to look at linear regression with indicator variables. So using the same hospital data set that we saw in the previous lab, now we're going to consider the example of, suppose a hospital is trying to set a benchmark goal of having patients report that nurses always communicate well at least 75% of the time. So now we can dichotomize that nurse always variable and break it up into two categories, less than 75% or greater than or equal to 75%, and we can use simple linear regression to further examine the relationship between the percentage of patients who always recommend the hospital and this dichotomized nurse communication. First thing we want to do is again state our model and look at exactly what linear regression model we're going to be talking about. So our outcome is exactly the same as it was in the previous tutorial. It's the percent of patients in a hospital, hospital I, who always recommend that hospital. And we have I equals 1 all the way. We have 3,570 different hospitals in our sample. Now our explanatory covariant, let's call it D. And we're going to define it as either 1 or 0. So if DI is equal to 1, that means that at least 75% of the patients in that hospital said that the nurse always communicates well. And if it's equal to 0, that would mean that less than 75% of the patients said that their nurse always communicated well. So YI is our outcome, DI is our explanatory covariant, and now we can write down our linear regression model as the outcome YI is equal to alpha plus beta times DI plus some residual error epsilon, or EI, and that follows a normal distribution with mean 0 and variance sigma squared. Now, an interesting thing to note here is that really this model is identical to a one-way ANOVA. We have two parameters in our model that we're trying to estimate, alpha and beta, and so there's two groups. We're estimating two group means, and we're assuming that the variance conditional on our covariate is equal to sigma squared. So we're assuming constant variance within groups. So it's identical to a one-way ANOVA with only two groups, or it's also identical to a two-sample t-test with equal variances. So essentially, the assumptions of this model are similar to those two tests. We assume that within categories of DI, that our outcome YI follows a normal distribution with constant variance. That's the homoscedasticity. Again, we need independence of our observations, so we have to assume that the observations are independent. And we don't really make a linearity assumption in this situation because we only have two values that DI can take on. We have one parameter for each value of DI, so this is what's called a saturated model. We're estimating the mean for all values that DI can take on. And we'll see a little bit more about this later. So now let's go ahead and open up Stata and fit the regression model. We fit the model in exactly the same way as we did in the previous tutorial. Our dependent variable is recommend yes, but our independent variable we now need to define. So before fitting any models, let's go ahead and define this dichotomous variable. First, we're going to generate a variable called hi nurse. We define hi nurse as 1 if nurse always is greater than or equal to 75, and we make sure that we assign a missing value to any missing values of nurse always. And then we define hi nurse is equal to 0 if nurse always is strictly less than 75. And once we've defined this hi nurse covariate, we can go ahead and fit our linear regression model in the same way as we did in the previous tutorial. The dependent variable is recommend yes. The independent variable is now hi nurse, and we can hit OK. So again, we just use this regress command to fit our regression models. There is a shortcut if you have indicator variables in Stata with more than one group. In our case, we only have one group, but I'm going to show you the shortcut anyways in case you ran into a categorical covariate with, say, 5 groups, and you wanted to fit those 5 groups as a categorical variable in a linear regression model. A shortcut in Stata is to say xi colon and to place that directly before the regress command. So I say xi colon, and then directly in front of my categorical covariate, I put I dot. And what that's going to do is it's going to tell Stata to go in and construct indicator variables for your categorical covariate. So if I look now in my variables list over here, Stata went in for me and constructed that indicator variable and then threw that indicator variable into a model. This becomes really useful when you have categorical covariates with a bunch of different groups. But since we only have two groups in our example, we can just use the standard notation and look at the output from that regression model. My estimate of alpha corresponds to this constant, and my estimate of beta goes along with the high nurse covariate. The fitted regression model is yi is equal to 62.86 plus beta, which is 9.98, times di plus some residual error. And that residual error follows a normal distribution with mean 0 and variance equal to 8.54 squared. Now let's go ahead and interpret the coefficients from this regression model. And I think the easiest way to interpret it is to first write down the mean of y when di is set to 1 and when it's set to 0. So when it's equal to 1, it would be equal to alpha hat plus beta hat times, and I would plug in 1 for di. This is actually an estimated mean, so I should put little hats over those to show that they're estimated. And then when di equals 0, it would be alpha hat plus beta hat times 0. So this term would cancel out because I'm multiplying by 0. And this now makes the interpretation of these parameters relatively straightforward. So alpha hat is the expected value of yi when di equals 0, or in more meaningful terms, it's the estimated average percent of patients who always recommend a hospital when less than 75% of the patients say that nurses always communicated well. This value is equal to 62.9%, or it's equal to alpha. Now moving on, looking at this expected value, the estimated expected value of yi when di equals 1, it's equal to alpha plus beta hat. So alpha plus beta hat is the average percent of patients who always recommend a hospital when at least 75% of the patients say that the nurses always communicated well. And alpha plus beta hat, this group mean, is equal to 72.9%. And if I were to take the difference of these two means, it would be alpha hat plus beta hat minus alpha hat, so it's just equal to beta hat. So in this case, I could say that comparing hospitals with at least 75% of the patients who say nurses always communicated well with those where less than 75% of the patients said that nurses always communicated well, the average difference in percent of patients who always recommend a hospital was approximately 10%, or beta. Now let's go ahead and perform a hypothesis test that this difference is equal to 0. Or I could just say, I can test the hypothesis, that beta equals 0. That this difference in means is equal to 0, versus the alternative that beta is not equal to 0. So to do that, I can just use the regression output for beta. I found that beta hat is about equal to 10%. The standard error, the estimated standard error of beta hat is 0.32. We can put those together, and we find that our t statistic is equal to 31.7. Now, under the null hypothesis, this t-statistic follows a t-distribution with 3568 degrees of freedom, and we find a p-value that's less than 0.001. So it's highly significant, and I conclude that yes, there is a difference. We have evidence that there is a difference between these two groups. And the average percent of patients who always recommend a hospital is greater when at least 75% of the patients in the hospital report that nurses always communicate well. The last thing I want to do in this tutorial is compare the results of the test above to a two-sample t-test with equal variances. You have to think back a few weeks. So I want a two-group mean comparison test. The variable name is recommend yes. The group variable name is high nurse. And if I look at the output from this t-test, I find that the estimated mean when high nurse is equal to 0 is 62.9. When it's equal to 1, it's 72.8. And the difference is equal to negative 9.98, or it's equal to beta. So this is exactly what we saw in our regression model. Further, the standard error of this difference is exactly equal to the standard error that we saw for beta, and the t-statistic is exactly the same. The null distribution of the t-statistic is the same, and the p-value, while we don't have enough digits to conclusively say this, the p-value is the same. So you should notice some striking similarities between the linear regression with one indicator variable and the t-test with equal variances. These two things are actually equivalent, so this is neat. We're just trying to tie together some concepts so that you really start to get a fundamental understanding of what goes on in statistics.